Yeah, I was hunting around for something to talk about this morning. No, I wasn't actually hunting around. Well, anyway. So I got Phil Beisel this morning. And the reason I have Phil Beisel this morning is because it's Saturday morning. And Phil and I are kind of getting started on maybe this is kind of almost a regular thing. Phil, there was a All In podcast last week where Elon was waxing a little more philosophically, even than he normally does.
Mhm.
And he got into a subject matter that has turned out to be like half of my shows the rest of the week is on inference. And I'm not sure that a year ago I knew what the definition of inference was when it comes to a computer. And even though I was using it every single day for like the last 60 years. But there was now inference is like a word that just slips off of our tongue quite easily. And it's taking on new meaning almost on a daily basis. Brian Wong and I last night did a video, and it didn't get seen by many people. I'm going to really recommend, I'll put a card up at the end. We talked about inference chips might be a bigger business than humanoid robots because you need an inference chip in every bot, you need an inference chip in every car, you need an inference chip in every tractor, you need an inference chip in everything that moves, and you need an inference chip in everything that doesn't move that has a computer a computer
A compute function.
compute function.
Yeah.
So it may be the biggest business of all, and maybe Tesla ends up with AI 6 being the leader in that as well, which Brian started talking about as early as I want to
Yeah.
say.
So he's been talking about that for a while.
Okay, so you though had a particular take on the inference part of it. In particular, a couple of actually takes. One with regard to kind of a philosophical aspect that Elon mentioned, and then one to more of a practical, uh, pragmatic aspect. And as you as an engineer, extremely interested. So I'm going to turn you loose, and from time to time, I might jump in and correct you. I mean, not.
You can jump in and stop me from talking endlessly.
All right. So talk to me about
Yeah.
what hit you.
Okay. So my first thought is if you haven't seen All In Podcast with Elon Musk, watch it and then watch it twice. Um, there's a lot of information in there. And I watched it once and I kind of just went, shh. And then I mean, what I mean by that isn't like went over my head, but it was like I wasn't really um, putting enough emphasis, enough boldness on the points he was making. There were a lot of interesting stuff he was saying. And one of the things I wanted to talk about in the topic of inference is, he was talking about the next chip architecture, and on deck is AI 5, right? So today, in all Tesla production vehicles, we have AI 4, hardware 4. It's been renamed. And you can notice, by the way, when I said that and I kind of had a little pause, watch the podcast. Elon does the same thing. He
Yeah, right.
he has this uncomfortableness about the fact that it's been renamed. Not, I think he's leaning in on the new name, but he's like, oh God, I don't really want to get into the description of that hardware 4 and AI 4 is the same thing. So I'll just kind of say our inference chip. Um, yeah. So what he was getting into was this idea that this chip is looking to be a superstar. It was really like he was very, very pleased, and you could tell by his body language that he's very pleased with the chip designers doing that chip. And what he was saying is, in certain cases we have 40x performance, we have 10 times the memory, 8x general performance increase over AI 4, and some of that is to be expected because all next generation chips going down to smaller node size. In other words, think of it as transistor gap, but smallest element, 2 nanometer, 3 nanometer, that kind of, we're dropping we're dropping the distance between the elements that to the actual action of compute, the transistor level of the chip. And when we reduce that space, we effectively can move signal faster, right? Because we're not dealing with signal only moves so fast. So what he was saying is this chip is turning out to be the superstar chip, and he's very pleased with it. And um, but I think the theme that I wanted to get into was the vertical integration side of this, which is what he was saying is that the software team and the hardware team work hand in hand in the same building, a couple cubes apart, to build this chip. And that's a meaningful thing for if you're a Tesla investor or you look at a competitive advantage for Tesla in general, because what he's saying is, look, there is this thing called FSD we built at Tesla, and it's a neural network, and it does a lot of matrix math operations, and then some other operations like softmax, which he talked about. Um, and maybe we could define that at some point. But what he's saying is, here's a set of operations that are done through FSD, and they're very common to FSD, and they're somewhat common to neural networks, but in general, they're what FSD needs to have at its core. And if they can run them faster and faster and faster, they get more inference cycles per second, right? And what does that lead to? Ultimately, it leads to, on one measure only, it leads to a safer FSD system. You know, if you can compute the trajectories, the things that you're going to, your trajectories, you can compute the obstacles at a faster rate, you end up with a better solution, right? So it's really important to understand what this vertical integration means. It means that this software team can look at every action that's done through their AI, from the vision coming in, vision data coming in, to the final outputs of the AI, the control side, and can understand exactly where it's lacking performance, where it's spending its time. Spending its time is the right way to think about it. It's like, how many compute cycles to do this? How many compute cycles to do this? And there's always these bottlenecks they find. And the one that Elon mentioned was the softmax algorithm. And without getting into the details, that just creates this probabilistic distribution of values at the end, which add to 100%. We'll keep it simple. It normalizes a set of data into a set of numbers that are percentages adding to 100%. And he was saying essentially that in AI, on the AI sort of hardware four boards in the current compute solution, that they've emulated that in software. Now, what does that mean to emulate something in software? By admission, it means that you don't have it in hardware, right? It's like you're saying, I want to put it in software because it is not in hardware. Mm-hmm. There's an article I wrote on accelerated computing where I talk about the math of an accelerated computing chip. I mean, what does it do? And then it does these matrix math operations. And by the way, as somebody who was partially a math major, also a computer science major, and had taken, this is many, many years ago, this course called linear algebra, where we did a bunch of matrix math operations. I think I was halfway through that course before I understand any application whatsoever of that. Like, a lot of the stuff is taught without application. And okay,
every math student says, when will I ever use this?
When will I ever use this? Well, it's 90% of everything you do in a neural network is linear algebra ops. So particularly matrix multiplication operations. And what I did in that article is I thought I would do something a little crazy, is I would take the matrix math. So in a NVIDIA processor training or inference, in the inference processors of Tesla, this matrix multiplication operation is sort of resonant on chip. The chip can load the data and do it in a resonant way, just like it can add two numbers. It can do the additions and multiplications kind of as a singular operation. Okay. All right. In other words, you've taken something out of potentially software. So what I did in that article is I actually wrote the C code that did matrix multiplication. I wrote the code. I just wrote the damn code, and I said, this is how you take one matrix and you multiply it by another, and you get the resulting matrix. And this is how many lines of C code it is, and you can see it. I wrote it there. And then I I compile it into machine code, and I display that as well. Now that may be way beyond uh, some people's understanding of what's going on here, but
You'd be mine.
well, what happens is what I'm getting at is the CPU or the GPU
Uh-huh.
has a set of primary instructions,
Mhm.
and some of them are logic. Some of them are just pure like math, and some of them are flow control. Like if this is true, then jump here, and the typical stuff that you find at a higher level coding language, except it gets implemented at a much lower level. And the expression of everything we do in compute has to translate these computer languages higher level, whether it's Python or C or Java or take your pick. It has to get it down to the machine code level, right? So I did that in the document. I wrote the C code, I wrote the machine code to be executed on a CPU, and I showed the number of instructions necessary to go through that. And kind of logically, each instruction takes one compute cycle. And so if you look at a processor and you say, oh, that's a 2 gigahertz processor, well, that gives you an idea how fast it can execute each instruction, right? So if you have this many instructions, I'm not going to give you a number, but let's say you have 100, it's going to take 100 units. If you have 200, it's going to take you 200 units and so forth. It's kind of a linear thing, roughly. So imagine that you take that operation and you kind of shift it onto the chip itself. You take all this code and you kind of condense it into a chip level thing. Now, that isn't to say it just simply magically the compute isn't happening. It is happening. But there's a difference in how it's happening. It's not taking a bunch of values and code and constantly loading the processor, and you're not dealing with this
Back and
still,
forth.
yeah, back and forth, this latency between memory to processor. You basically shifted it all right to the core.
Mhm.
And so when Elon was talking about softmax, that was his favorite example that he could think of at that moment, where he's saying, well, in hardware 4, the team had to write that in C code, and it's executing on the co-resonant CPU because we don't have any hardware support for it in the GPU, right? So what he's saying, he's saying, I'm excited because in AI 5, the software team has taken a lot of that function and they've onboarded it right to chip.
Mhm.
So, which means that now they can run their inference cycles maybe faster instead of 15 times a second, they can get it to 30 times a second. Or if they're running at 30, they can jump it to 60 or 90, leads to a safer system.
Yeah.
Just better performance, right? And better performance means other things too. It means that the thing consumes less power. It's doing less movement of data and all this other stuff. So therefore it consumes less power. So it's more efficient. It's more performant. It's more efficient.
Mhm.
And this is what he's excited about. He's saying at Tesla, we're doing this in a vertically integrated way.
Right.
We're saying that the chip team, part of the hardware group, um, and the software team are co-resident in the same building.
Right.
They sit and talk all the time, and the software team says, "This is what we really need to make this thing
Mhm.
really hum."
Mhm.
And that is obviously very, very different than almost everybody else out there. In fact, there is no legacy automaker doing its own chip. There is no progressive automaker doing its own chip. Tesla's kind of the standout here, to my knowledge, and that would include everything like from Waymo to they're doing their own chip. And so not only is it important to get that performance, um, but I think it just gives them so much more flexibility as they run this out. And you're going to see that this idea of them getting deep into this inference thing is going to be a theme for the next 15 years at Tesla. It is going to be when I first heard that they were doing AI 6, which is the follow-on to AI 5, you got to start these things in overlapping, while you're,
Sure. 100%.
yeah, while you're getting AI5 into production, testing it, getting samples, and going to, a full production fab, you're starting your AI6 program on top of that.
Yes.
Just like, Apple's doing, there's members of the engineering team working on the new OS, iOS versus the current one, concurrently. And it's always hard to break off these guys because half of these guys are the guys that worked over here.
Right, right, right.
It's like there's like the same team, and not everybody wants to necessarily peel off into the new team, although that's a theme, because they really want to make the product that they've worked on, the best it can be. And that usually means you got to babysit it to the finish line.
Mm-hmm, mm-hmm.
Right.
Yep.
But so, you've heard Elon say, hey, I want to go into this thing called AI6, and I'm going to go suck up an entire fab, by Samsung. This theme is going to pull forward immensely. And I think there's another part in the All In podcast where he talks about Optimus, and he talks about the compute, and he gives some crazy number like $6,000 for cost
For the chip.
Yeah, that's something's wrong with that. I don't know what is wrong with that, but there's something.
Good. I'm glad you're saying that, because that's been a recurring theme for the last 2 days on this channel.
Yeah,
What are we going? How going from $1,000 now? I even asked Grok. Grok says, "Yeah, you're right, Randy. Everybody pretty much thinks that the current chip is about $1,000 cost of goods."
Yeah.
And now he's talking about something that would be $5,000 to $6,000 cost of goods for Optimus. A, what would be the difference that would cause it to be that expensive? But B, what would we get for that? What would be the dramatic change? Now, Brian Wong tried to explain that to me last night, that there could be some pretty dramatic changes in 6 that would make it worth the 5,000 in terms of the thing
Right.
that you would get, you could actually monetize. But the other question that we didn't really get to is what would cost 5 times as much?
Yeah, well, I'm not going to give you that answer because
Okay.
it's still a gap in my thinking about
All right.
where the cost would be. And I don't know if Elon misspoke, and usually he doesn't,
Yes, right.
or he's talking about a bit of apples to oranges. In other words, he's pulling in other costs into maybe he's talking about all hardware cost at the component chip level, boards, ECUs, maybe like the full ECU. Sorry, ECUs are like electronic control units,
Right.
and those are kind of like the fundamental boards that we see in these things. Like in a MacBook, it might be called a motherboard, but on a vehicle or in an Optimus, you would call it an ECU, because we invent a lot of silly terms. And
So would there have to be a lot more expense on those if you've got 60 actuators versus if you only have 20 actuators?
well, at that level, possibly only because you're pulling back. You have more compute and more different circuitry involved. I'm just talking. I think he's just trying to draw a box around the electronic circuitry of the unit.
All right,
Not
so we don't have that answer.
no, and it's I kind of my eyes popped open because I was like, that's it's a big cost. It is and it isn't. I feel like one of the realities of it is that we may have the other side of the cost wrong, and
Okay.
may have had that wrong for quite some time.
Okay.
I can say that without being specific. My work at Rivian, these boards are very expensive to bring up. In some sense, Rivian, did not have the benefit. Rivian did in-house hardware, but did not have the benefit of, when you go and you've got to purchase all the component chips on the board.
Yeah.
And in his case, in the case of Rivian's just too small to do chip design, so it can't do the thing that Tesla was we're talking about, vertically integrated, full on. Let's go build a chip.
Right.
Remember that chip's got to sit on something.
Yeah.
So if you're Rivian, you got to buy it from NVIDIA or somebody. If you're Tesla, you're buying it from yourself, whatever that means. It's, in other words, it's the lowest cost option, minus the R&D cost, but that's capitalized differently, right, on the balance sheet. So at the end of the day, I know that these boards cost a lot of money. They're very specialty. Like if you look at your favorite MacBook running up to I don't know, 3,000 plus dollars. I mean,
Yeah,
a lot of that is in fact
the
the
chip.
the motherboard. Yeah, the motherboard, and it's and the SoC, and so it's somewhere between those costs. And I don't know whether he's estimating high and pulling in other stuff, or the previous estimates have been low.
Yes, right.
I'm sorry, I can't answer your question.
All right, so let's go back though to your initial idea because I want to flesh it out for those of us who are not as computer savvy, and take it out of maybe the computer jargon side and bring it into the practical side. So software, I'm on the software side of the team. I'm closer to the use. I'm closer to the practical side of what's taking than the hardware guy is. I'm trying to be that. I think maybe I could describe it as the middleman between somebody that actually is controlling levers, controlling motors, trying to make those ECU applications. So what is the software guy doing to try what's this? We've talked about it 1,000 times on this channel going back years, that Tesla's vertical integration and
Mm.
their idea that all of the engineers and all of the actual executors all work on the same floor and all talk to each other all the time.
Mhm.
How does this advantage, which is I think your theme today, how does this advantage particularly impact this software hardware convergence on the inference?
Yeah. Well, I mean, I think what is true here is that, software, I mean, we call these software um, sort of software architected software design systems. In other words, it's sort of the software itself that controls the entire flow.
Right.
It's sort of the logic layer. I mean, whether you call it an AI or not, it's kind of irrelevant. I mean, it's a, if in like in full self-driving, if you think about it, you have input and you have output, and the middle thing is called a function, and that is true in just at math alone, right? In
Yep.
math,
Yep.
input, function, output. Okay, so traditionally, traditional software approach, algorithmic, is that this function was a large body of code written by a team of software engineers. Today, in the case of FSD, this function is a neural network architected by a set of software engineers who have developed a certain technique of the of the interior of this. It's not a neural network isn't a just a thing. It is a definition of a set of levers in how it comes together, and layers and parameters and biases, and we can go on. But it's not just a thing. It is a specialized. It's sort of the building blocks at which this software team has taken, developed a technique and how they wanted their model to work, and then they've trained that model and created this driving function through AI. So it's really the software team that's the driver in this equation. It's the one, for being very pun worthy, it's the one in the driver's seat.
For sure.
Okay. And of course, coming from a software guy's perspective, you're going to see me say this, but software drives hardware.
So, so later today we will have a hardware guy on. No, I'm sorry.
Yeah. No, I mean, software drives hardware. I mean, if you go back,
Yeah, of course.
uh,
I think we can agree on that.
certainly, because software is connected to function,
Right.
right? I mean, hardware by itself, I mean, once you integrate certain elements into hardware, you can say they run function, but it's really a software team, and software is the glue of everything here that determines, okay, what are we trying to do? What's the problem we're trying to solve? Oh, we're trying to solve the fact that we want this car to drive itself. Okay, what does that mean? Oh, okay, we have a set of sensors and we have some set of outputs that lead to accelerator, braking, steering angle, and we've got to figure out something in the middle that makes this data this input yield proper outputs. Okay. And so software does drive, and therefore, but software does get hung up because traditionally your hardware team isn't co-resident and is kind of over there. When I say over there, there's different definitions of that. When I was at Rivian, we were together. I mean, I ran software, and my friend Greg ran hardware, and he um, he responded directly to the types of things we wanted with constraint. Obviously, there's always constraint. There's always back and forth. Software guys always ask for a lot, and hardware guys are always saying no. And that's largely because of cost. I mean, it's oh, I want memory. Oh, I want the fastest possible memory. Well, the fastest possible memory is twice the cost of this memory. And then so somebody's got to pull back and look at, and then the software guys always have a hard job in the sense of proving their use case, meaning like, well, why do I need that much? You know, um, somebody at maybe an exec level is looking at it going, okay, this board that I thought was going to cost 1,000 is now 4,000. What did you do? And the hardware guy can say, well, the software guys say they need all of this compute, and they need it fast, and they need it this, and they want the best chip at the highest, they want, um, and you pay premium for, it's like a non-linear relationship. You pay a premium for the best hardware. Um, so the software guys, not only design the function, but they also sort of take some principal blame because they're always asked this fundamental question: well, why do you need all the compute? And at the end of the day, the funniest thing happens. Whatever compute is given, the software team largely takes up.
Uses every bit of it. Yes.
Yeah. Um,
And then some.
and then some. And what's interesting is the difference between a good software team and an ordinary software team is that a good software team not only solves the problem, but also knows how to optimize to the hardware, right? And one of the things that happens in FSD that people probably don't even think about is they just think they train a neural network and they throw, and maybe they do some testing or something and throw it out on the car. And I'd say there's a lot there. There's a lot not there in that simplistic description. There, half of the team, software team, is looking literally at reducing the latency through the system and trying to get the Elon would say best photon to control latency, where it take in visual data and get controls, and they're trying to reduce that latency and not spend silly cycles, and that's why he was complaining about softmax to full circle this, um, and ultimately a good software team is optimizing, and ultimately, and a good software team optimizes as they develop. They don't just get to the finish line and say it's time to optimize, but they often get to the finish line and realize that it's also time to optimize. Like it doesn't, that process um, never goes away.
Yep.
It's like, and then the hardware team can either have an overwhelming amount of hardware support for that software function, which never happens, or it can meet you halfway, and then you as the software, you've got to kind of say, well, I have to fit within some real world constraints. And when that happens, kind of on a longer scale of development, meaning version to version, across years and years with a program like FSD, what you'll see is, okay, what do we need in the next generation? I mean, why are we doing AI 5? We have AI 4. It's supposedly good enough. Well, it is good enough for what is defined today. The software team is saying, but I want to do these things. And maybe in some companies that might be marketing driven or whatever, but let's just say the software team as the starting point here to keep it simple. I want to do these functions, and the hardware team is saying, well, on AI 4 or that's not possible. We need to give you something else. So they envision a new chip, and that's why AI 6, right? You see the future of this, and you go, a vehicle could you could drop version 14, and we soon will drop Tesla will drop version 14 on the vehicles running on hardware 4, and it will be safer than a human by some factoring of 2 to 10 or something. And then they'll be able to squeeze a little bit more out of that, but probably not a version 15. Now, I'm not saying that with some kind of authority, and I don't know, but probably not a version 15, right? So version 15 will probably be on AI 5, and what will fit on AI 5? Probably the AI 5 will survive as the production chip for 2 to 3 years before AI 6 replaces it. So maybe you've got a version 15, 16, 17 of, but remember, these versions aren't just the linear way of thinking is these versions are just improving the safety factor of driving. It's not about FSD is going to explode into a whole bunch of other inference use cases that we've talked a little bit about previously, like full integration of resonant voice interface, Grok on board, interlaced or running co-resonant with the FSD. And then the FSD use cases themselves will explode to using vision data for things that are just beyond the scope of the narrow scope of just driving the car. We'll be using the vision stack here for doing all sorts of use cases about, optimizations of how robotaxi runs through the city, and then just other use cases based on achieving. We've gone through them. I'm just trying not to jump.
Yeah. In fact, I want to add one to your list in case you didn't listen to Brian.
Sure.
One that Brian suggested was that Elon is definitely looking at this as a future inference in the cloud. Not in the cloud is the wrong way to say it. A future resource for a distributed inference that would be purchased from the owner of the car or be used by.
Yeah. I mean, the interesting thing, a vehicle platform is a super interesting platform to put inference on, because these chips we're talking about, AI 5, AI 6, these are in a class of more power hungry chips that need better energy environments. These are not cell phone chips by their very design. A cell phone maybe maximum draws about 15 watts, and we can't sustain that, or it would get super hot and the battery would just, tank right away, or it would get so hot that it would shut itself down. So we do that a little bit, like on iOS, you'd see that in maybe some gaming use cases where there's the way to look at the processor, the draw, and you could say, okay, it's drawing this much power off the system. And on a cell phone, I'm going to ballpark it 15 watts being kind of like top end. On AI 4, I think top end draws about 160. AI 5, I don't think we know, but I've heard and written up to 800.
Wow.
Yeah. So I mean, here's the thing about this: if you have power available, you can put it to good use in something called compute, right? So there's nothing, NVIDIA chips are running 800 plus watts in training, and there's nothing wrong with that. It's just that forces you to have a lot of power available. So in a vehicle, so now you've got a chip that's in a different class here, right? A chip that can do a lot of inference operations by AI 6, sort of at the class of some of these larger inference platform chips. I mean, literally at the class of like, yeah, like a
1800 or something.
yeah, absolutely. Actually, passing that, I think. But so given that, you need a power rich environment. So you need to have a lot of energy density to draw out, and a vehicle is perfect for that in a sense, because the two vehicles sitting in my garage, which are both electric. One's a Rivian, one's a Tesla. When I add the batteries together, I think we're at 225 kilowatt hours or something like that. And that could power my house for, you know, uh, 8 days, 7 or 8 days, right? So there's a lot of energy store there for that. So when you think about distributed inference, it is as if what we're saying here is you've taken um, what is normally at the data center in one spot, with one power source, if you will, and you've pushed it out or distributed it. That's the term. And you've got a inference rich environment on the car, and then therefore you can distribute inference tasks to the car. And there's some economic, reality there that you bought the car and it's your energy you put input into the car. So ultimately the fixed cost is the purchase of the car, and the kind of uh, non-fixed cost would be, energy. And so while the car sits idle, which, as I mentioned, my two cars are sitting in the garage at this moment and they're sitting idle, they can be available inference machines. And that's important because you wouldn't do it in training, because training requires
Mhm.
kind of a coherent compute cluster where everybody's acting together, and you can't have nodes coming and going. Like imagine my using my car for inference, and what it's doing is it's doing some grok query for XAI, and I want to get in my car and drive. And at that point, they shut down inference and move, because I'm using the energy to move these things called the wheels of a car. At that time, my compute node goes offline. It's not available.
Right.
So, but there's plenty of others to choose from, right, that are opted into this program. So absolutely, distribute. The article I wrote on said inference is going to explode. There's a chart at the very end, and it's a kind of a lean-in chart to the next 5+ years. And what it does show is that edge-based inference is the piece that's really going to explode here.
I thought we
And
kind of talked about that last.
we did, yeah, we did. And the edge includes the actual runtime use cases of Optimus, in other words, embodied autonomy or embodied AI, sorry, embodied AI, Optimus, FSD, two types of robots that are out there. But distributed inference is an edge case, edge compute case.
Right. Okay. All right. So what I want to do right now is I want to tease our second show, because I think it's a completely separate subject. And so I'd like to do it as a second show. Elon Musk also mentioned on two different occasions now that he wants to rewrite the corpus of human history. So on our second show, we're going to talk about rewriting the corpus of human history. So Phil Beisel, thank you so much for being on the
Yeah.
show. People, you should follow him on X if you're not already doing that. So look him up. It's really easy. You just look for his name, Phil Beisel, because there's no other. He's solo. He gets that name all to himself.
Yeah, I'm a legend in my own mind.
Unlike Randy Kirk, where there's many, many, many of us. I mean, that's almost a dime a dozen. All right, Phil, we will go on to show 2. Thank you so much for being on this Saturday morning.